Welcome to our magnetic levitation of graphite final presentation by Alyssa and Roxanne. Our goal of our project is to get our pencil lead, our diamagnetic graphite, to levitate on a bed of magnets oriented in a north-south checkerboard pattern of the same shape, volume, and strength. By orienting the magnets in a specific pattern, it would, in theory, interact with the graphite in a way where it would find equilibrium by hovering ever so slightly on this bed of magnets. And originally, playing with the magnets, we discovered very quickly the power of magnetic repulsion, as shown in the video. This got us very excited about our project. And originally, we were going to actually cut down these magnets so that they were like the same size, shape, and strength, but that would have been a big hassle, and we also would have had to cut them down with something non-metal so it wouldn't have affected the magnetic field, so we would have had to use the water jet, which just seemed really scary and inefficient. And then Curtis ended up supplying us with a variety of like flat cylindrical magnets, which were honestly, they worked very well. They were like all of the same strength pretty much, but we just had a variety of different sizes, which was really cool.
So then we tried out different varying shapes of our magnetic field and dimensions. So this was one of our first ones where we did a 7x7 on the bottom, and then we didn't have enough to do a full second layer, so we did a 3x3 in the middle. As you can see, it did not get the graphite to levitate, and we figured that was because the magnetic field was too big for the size of graphite and not uniform enough for it to actually act upon the graphite the way we wanted it to.
For the second field we tried to do, it was a 2x2, and it was just like 14 high, which we thought was going to be really cool by like making the strength super good, but it turns out that like the farther the graphite actually is from the base magnets can't actually like interact too much with the graphite at the top, so the farther you were away from the base of the magnet, like the base wasn't acting as much on the graphite, so the distance did play a key role in this.
And then we came to our final option where it was a 4x4x4, and we took the lesson from our previous options and we made it closer to the base level of magnets to strengthen the magnetic field and how it acts on the graphite, and we made it slightly larger than the 2x2 but smaller than the 7x7, which amplified the magnetic field in a very stable way for the graphite.
And then here are some demonstrations of the graphite jumping from slight disturbances on the bed of magnets to see the full effect of this levitation. Yeah, so when I was like poking around, it was just kind of jumping all over the bed of magnets because it really just wanted to be at its equilibrium point. And like tapping it was really easy because there was like basically no friction because it was levitating, and the only friction was coming from like air resistance and like when it was like just like touching, when it was like that not perfectly like zero B field, when some of them are a little bit different strengths.
So then we have our predicted, our slight prediction math equations where we're trying to figure out what would our ideal delta B be versus our actual delta B. So our ideal delta B would be that all of the magnets would cancel each other out and the change of B field would end up being zero. However, we don't live in an ideal world, and so we wanted to do some calculations for what our percent error was due to humans and or machine error. We did find that our average B fields were good for equations because our percent error was below 2%. So then we have our measured and predicted mathematical equations. We combined them into the same thing because we weren't given a predicted strength of the magnets when we were given the magnets, so all of our measurements when it came to B field was due to average measured magnetic fields that we found. The only one that we were able to do a comparison of was our mass for our graphite, but they came out to be 0.00001% different, so we considered them basically the same for our calculation purposes. So we first found the mass through density times volume, which matched up perfectly, and then we used the mass to find the gravitational force and the normal force, which made sense during our sanity check that that's the force that it would come out with. And then we found the average B field for a single magnet, and then the average B field for the total magnetic field by multiplying the single magnet by 16, which came out to be something that made a lot of sense for us. And then we used the F equals ILB equation, but because we didn't have a current, we considered I negligible and used F equals LB, which we then equated to F equals HB to find the height of the graphite above the magnets, and we found that it was about 0.053 millimeters, which we thought made a lot of sense for what we were seeing.
Mm-hmm. And then here's our diagram. It's on there, but it's also right here. We have our oscillating, or our different like north-south magnets, and then the inner 4 here kind of like actually do the levitation and push it up, and then these 12 on the outside kind of help with stability, keeping it in the center. And then these like these different like north-south ones, the B field goes in and then it goes out, and then it goes in and then it goes out, which keeps this graphite happily floating, which this is kind of like an exaggerated model. And then the equilibrium point exists where the gravity wants to pull down, and then the B field pushes it up, and it finds happiness at this 0.053 millimeters above the magnets.
So this is our final project that we ended up getting to work. There's the picture here, which you saw earlier. The video is just showing it bouncing around again as seen earlier, but fully levitating above the magnets this time.
Mm-hmm.
So how it works is the graphite, if graphite doesn't have iron in it, it's diamagnetic, which means that if you have 2 opposite ends of a magnet near it, it doesn't want to be there, so it jumps away. We also took into consideration that we do have tape and water in our final working experiment, but the tape is non-conductive, so it doesn't interact with the magnetic field. And while the water is slightly diamagnetic, it only affects the magnetic field by 0.001%, so we considered it completely negligible in our calculations. And then having magnets amplified by multiple magnets in a specific north pole, south pole checkerboard pattern allows for levitation and stability when introduced with a diamagnetic piece of graphite.
Yeah. Also, our take-home message is that it takes a lot of trial and error. As long as you understand the concept behind what you're trying to do, you can succeed at any project. It just might take several tries. Also, celebrate even all of your small successes.
To keep yourself sane. Thank you for listening to our levitation presentation. Perfect, we went 10 seconds over.
That's literally fine.
Oh my gosh.
Is she doing it?
I think so. You gotta move it around a little bit. It's like mildly hard to tell with the tape. Yeah.
It is?
Yeah.